Everything going here. So one thing is that I originally talked about having tests on Monday, but I've decided to make it Wednesday because I don't think we'll have enough material covered. So it'll be next Wednesday. It'll be through section 2.2, which we may get through most of today. If not, what you'll do on Monday, well, because you didn't have class Monday, the Tuesday, Thursday class is ahead of you, is going to be ahead of you. So I'm just going to let you view their class, their Thursday class for Monday. And then we'll have the test on Wednesday. That'll give you time if you have questions before the test, like Tuesday, then you can come and talk to me. I'll put together a review video probably Friday, because by the time, I can't do it Monday because I'm not going to be in any state to do a video, and Tuesday I'll be too late, later than I'd like. So if you want to watch it this weekend, you can, or you can watch it anytime before Wednesday. You can watch the review video. It'll be chapter 1 and chapter 2 through section 2. Well, Monday we'll actually cover some more material, but the review video will be separate from the class. So there'll be a class video, and then there'll be a review video that you can watch. It'll probably be half an hour. And you can bring in a cheat sheet. So I do that. And you want to keep the cheat sheet because by the time when you take the exam, you'll be able to bring in all your sheets from your previous tests. You won't have to redo everything. So you get, if we do 4 tests, you might get 4 test cheat sheets plus one additional one, depending upon where I finish relative to, if the last test covers everything, but if I have some material that's not covered by the last test that's included in the exam, then you'll get some more chance to do it. The first test is pretty easy, so you might get done fairly quickly. What we'll do on Wednesday, I'm not going to give you the whole class to take the test because you just don't need that much time. So what we'll do on Wednesday is the first 30 minutes will be class, and then the last 45 minutes I'll let you take the test, and then when you finish the test, if you finish early, you can just leave. I don't know exactly. I have to look back at it. It's probably 15, but people who know what they're doing usually finish in about 30 minutes, so it's not so even. Okay, so let me go get the people who came in later today. So we have Harmonies here, and we have Timber. And let's see who else. Miranda, I don't see Miranda. Oh, there you are, Miranda. Sorry, I keep looking for you a row ahead of the place. Okay, Miranda is here. I don't know why I expect you in the second row. And Kayla V's online. And only who that person was Caitlin. Caitlin Byer is not here. Okay. And Carrie. Carrie here. I don't see Carrie either. Okay. Okay, so what we're going to do is we're going to continue on in section 1, and we're just going to go through some examples that are in the back of the book, like your homework problems, and we'll talk about the significance as we go along. So this particular one says list all elements of each set. What that means is you list as a set, so use the brackets, everything that's described either by words in the case of problem number 10 or by using the abbreviated notation for 13. So this problem, what we do is we'd use the squiggly brackets, and we want to have all whole numbers greater than 8 and less than 18. So we have to be careful that we read the problem correctly. It says greater than 8, so we do not include 8. And then we just go listing all the whole numbers until we get to less than 18, which would be 17. So the mistake people make on these kinds of problems, they see 8 and 18, and they include 8 and 18, but because it doesn't say, we'd have to say the set of all whole numbers greater than or equal to 8 and less than or equal to 18 if we wanted to conclude them. Okay, now for problems like this, what they're looking for is for you to first identify what the pattern is, which looking at the first 3 numbers, you'd say, well, it looks like I'm just increasing each subsequent number by 1, and therefore I would use my inductive reasoning here that the next number will be 9, 10, 11, and so forth, all the way up to 14. So we just, basically what they're looking for here is to list everything, including the ones that I've represented as dots, and that would be as such. So that one's pretty easy. You know, up here, I could have, this is not what they're looking for, but I could have represented this instead of words. I could have said 9, 10, 11, ... 17, little curly brackets. So if I saw this, I would write that. And if I see the words, I would write that. Or I could use set builder notation, which would have x colon x, the set of all whole numbers greater than 8 and less than 18. So those would be the different ways that you might see the same information. And they're not always just the numbers listed in sequence. This one, we would have to again look at the pattern and see what that is. And you might initially think, oh, it's just counting by 2s, but then you get to the third number and say, okay, that's not working. So you'd say, well, that looks like 4 is twice 2, 8 is twice 4. So it's just doubling every subsequent number. And you would do that until you get to 256. I don't know why it does that. Oh, really? Oh, okay. Oh, so it's this thing. It's not me. It bothers me. I think something's wrong. I get all worried. Okay. Most of my classes are in the big tiered classroom, so that never happens here. It's new projectors, I guess. This is still section 1, yep. So that would be the correct answer. Okay. Okay. The next thing they ask you, what we're doing here is it says denote each set by the listing method, which is, and you might say, well, is this the listing method? Well, actually, what this is the list. So this says list all elements. We don't want to list all elements here because all elements may be a heck of a lot of numbers. So we want to represent them more like this. So these are using the listing method in 13 and 17, and then we're listing all the elements using the listing method. So obviously we don't want to list 700 integers between -200 and 500. So we're going to create a pattern that we can recognize, and then we're going to go ... and then we're going to put the last number that puts the limit. So I'm going to show you what mistake people make, and don't write this down. We'll get the right one. And you're going to explain to me why this is wrong. Okay, so why is that wrong? Yeah, I know it's partially because I'm wearing the headphones, partially because you're quiet. So yes, I do have reasonably good hearing. So yeah, it says between. It doesn't say including, so the same thing. So what we would do is we would start at negative 199, and we would end at 499. So this is wrong. What's correct is, and actually, yeah, I got to make sure I put the negatives. There's another thing that people do, which I guess is not technically incorrect, but it's not exactly what I would. So this is don't write this one down. You can write this one down. That's the right answer. Okay. Okay. So it's telling us the same information. Why don't I include 497, 498? Yes. So the first three establish the pattern. We need one number at the end. So it's overkill. It's superfluous, and it's taking up space. So we wouldn't do that. So we only need one number at the end to finish the thing off. Okay. Okay, so the next one is using the listing. This is what's it called? List set builder notation. So this says the set of all x such that x is a positive multiple of 5. So a multiple of 5 is going to be you establish the pattern with 3 numbers, 5, 10, 15. So multiples are the number, say multiples of 5 are 5 times 1, 5 times 2, so it's 5 times the counting numbers. Once you've established the pattern, then you put dot, 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 and because it doesn't set any upper limit, you just put a bracket. If it said x such that x is a positive multiple of 5, up to and including 125, you put 125 at the end, but there is no upper limit specified. So subsequently, the next one, 28, would be this is integer powers. So integer powers of 4, that would be 4 to the first, 4 to the second power, 4 to the third power, which would be 4, 16, 64, comma, dot, 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 close the bracket. So again, because there is no upper limit specified, then you just have dot, dot, dots. Now, I'm not sure if I've mentioned it formally or not. If you have a set that has a finite number, meaning, so finite just means it's not infinite. There's a certain number of them. It can be a large number, but it's not unbounded. That's called a finite set. So all of these are examples of finite sets. This is also a finite set. These two are infinite sets because they go on forever. So some of your homework problems ask that question, so when we get to that, you'll be able to answer the question. Now, let me pose a problem slightly different than this last one. If I were to say this, so x, this is a set of all x such that x is a integer power of 4. So I've taken the positive off of there. So positive means it's 1, 2, 3, 4, 5, etc. So we have 4 to the first, 4 to the second, 4 to the third, dot, 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 dot. So that means if you take the positive off, that means they could be negative integer powers, or they could be 0. It could be, to the 0 power. This is a little review on exponents, which we'll talk about later formally, but this is your little informal review of powers. So if I were to write this, I'd do dot, 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 because it gets smaller and smaller and smaller. And what I would have is, say, 4 to the negative 2 power, 4 to the negative 1 power, 4 to the 0 power, 4 to the first power, 4 to the second power, and then dot, dot, dot. I need more numbers there just to establish the pattern. Otherwise, it's not gonna work. So we've already done these. This is 4. This is 16. Dot, dot, dot. Does anybody know what 4 to the 0 power is? Or any number to the 0 power? Pardon me? 1? Everybody agree with that? No, 4 to the, any number to the 0 power is 1. But you may say, what is the 0 power? Because I know 4 to the first power means I have 4. 4 to the second power has 4 times 4, and that's easy to visualize. So why is something to the 0 power 1? Because what does that mean? Because you think it's not there, so that's why you think it might be 0. It's because that works out mathematically in terms of things that involve rules that involve something to a power. So if you took higher level math, you find out that certain rules apply to certain exponents and where the exponent varies. So 4 to the 0 power is 1. Anybody know what 4 to the negative 1 power is? Somebody said the right answer. Who was that? Okay, Miranda, right? Yeah. So it's 1/4, and that's because when you have a negative exponent, what that means is you can rewrite this as a positive exponent by putting in the denominator of a rational expression. So 4 to the negative 1 is 1 divided by 4 to the positive 1. 4 to the positive 1 is 4, so you get 1/4. So 4 to the negative 2 power would be 1/16. It's 1 over whatever these are right here. And then you put dot, dot, dot. Okay. So that's what it would look like if it was integer powers of 4. You can also see why this makes more sense now, because if you had 0, you go 16, 4, 0, and then you'd go to these fractions. But these all get sequentially smaller in this direction and larger in that direction. So these just become smaller and smaller fractions. But if I only showed, if I only showed 3 of them, you wouldn't know that I need to include negative powers of the exponent. Anyway, so that's, you're not going to get anything that complicated, but like I said, I try to weave in a little bit of review as we go along. Okay. This one says, denote each set by set builder notation using X as the variable. There may be more than one correct answer. So the question is, how do you describe with words what's happening here? So what do you think the next number after 5 is? 7. Yeah, it's just going to be the odd numbers. So you want to use odd number in your description. How would we describe going from 1 to 75? We could say all numbers greater than 0 and less than 76. We could say all numbers greater than or equal to 1. But all numbers, that's kind of vague. What kind of number is it? What's that? Odd numbers, yeah. And also, there's no 3.5 in there, so that would be whole. Yeah, we could call them whole numbers. We could call them positive integers. We could call them counting numbers. So there's a whole bunch of different ways of describing the kind of numbers they are, and that's why there's more than one answer. So we'll use whole number. Sounds like a good thing. whole numbers include 0. So this is how I'm going to say it, and you could say it slightly different, but it would look something like this. And I forgot one part, the odd part, okay, is an odd whole number greater than 0 and so it's greater than 0, so it's not equal to 0. It's less than 76 because it's not equal to 76. You wouldn't have to include greater than 0. If you did a counting number, which starts with 1, you could just say X is a counting number less than 76. You could take less, because you wouldn't have to, or is an odd counting number. Okay, so it says give a word description for each set. There may be more than one correct answer. So what does that look like? Yeah, states. So you could say, we're not using set builder notation, so you would just say the set of all United States. That would be all you'd have to say, right? Now somebody said alphabetical order in the other class, but it doesn't. We have to do it in alphabetical order for you to recognize the pattern, but if we wanted to list every 50 state, we could list them in any order because the order is not important when it comes to sets. It's important here because otherwise, if you didn't list them in order, you wouldn't know that it's all states. You kind of make that assumption. So. Okay, so we talked about finite and infinite sets. One of these is finite, one of them is infinite. So what's the first? Justin. Is the first one finite or infinite? Yes, Justin. Yes, finite. That's because there's a limit to them. There are a lot of numbers. There are 466 numbers, but 466 is a number. So this one is finite. This is infinite. And to be an infinite set, you just have to have dot dots on one side or both sides. So if I had just started with a negative 100, negative 80, negative 60, blah, 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 dot, 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 that still would be infinite. So this one here is also infinite. Do you think there are more elements in the second infinite set than the first infinite set? Because this one, there's 20 difference between each number. Here, there's 1 difference between each other. So you might think there's more in the second set, right? The answer would be no. Okay, because since they go to infinity, it doesn't really matter You know, infinite is not a number. Infinite is just the lack of having a number. It's unbounded. So they're both still infinite. They don't have the same number of elements because they have an unbounded amount of elements, which isn't so. There's a different. Sometimes people think infinity is a number, but infinity is means there's no bound to the amount of numbers. It's kind of like time, you know. Is time infinite? Is time finite? What's that? Finite? For us, it's finite. Well, it depends on what your religious beliefs are, I guess. Our mortal lives are finite. We would be. This is a set notation for our life here, depending upon your religious beliefs. So this is for atheists. That's the atheist set. This is the Christian set. Okay. This is your Hindu set. Maybe, I don't know. I don't know if that's true or not. I don't know enough about religions, but okay. Brackets and dots. I don't know. Yeah, I don't know. Do we exist at all, or are we just okay? Okay. So this is just to remind me. So these things that we've been talking about here, these numbers, these are members of a set. Okay. If something is not a member of a set, then what do we mean? Well, so let me just, we would say, let me just write it out. 5 is not a member of the set okay. So you'd say 6 is a member of the set. 5 is not a member of the set. That's just the terminology that we use when we're talking about members belonging to a set or not belonging to a set. Okay, so here's our exercise for verifying attendance. And so what I'm going to ask you, we were talking about set notation. And so what we would do, let's say we have set A, and we use this bracket, and let's look at just odd numbers. And then if you establish a pattern, you can just put dot, dot, dot like this. And then say up to 31, all the odd numbers, starting at 1 going to 31. So the question I have for you is 4, 7, 12, and 16, are these members of this set? So what I want you to do is to write the number 4, and then you write yes or no. 7, yes or no. So are these, is 4 a member of set A, or an element? Okay, we have actually talked about some of these things, but just to review, these different kinds of numbers. So the counting numbers or whole numbers, actually not whole numbers, I said that wrong. Counting numbers or natural numbers are numbers you can count on your fingers, but not like this. You know, 1, 2, 3, 4. You don't go 0. You usually go 1, 2, 3, 4. Okay, so those are counting numbers. Whole numbers include 0. Then you have integers, which can be positive or negative, but they are all whole steps, and you can represent those as equally spaced distances on a number line, both going from 0 one side and 0 the other side. So those are integers. Then you have rational numbers, which are ratios or fractions ratios of integers. So as examples, they're showing 3/5. So 3 is an integer, 5 is an integer. -7/9, so that could be -7 divided by 9 or 7 divided by -9, doesn't really matter. Even 5 is 5 divided by 1, so it doesn't have to be a fraction that doesn't simplify. And 0 divided by 1 or 0 divided by anything is going to give you, by any integer, is going to be 0. And it turns out that if you have a rational number, we'll learn more about this later, rational numbers are either in where you have what we call a terminating decimal, and that means that we have a finite number of place holdings in our results. So 1 divided by 4, 1/4 is 0.25, and then you get a lot of zeros, but it's terminating. So, but all the other ones, for example, 2 divided by 3 is 0.666666666. So it keeps on, and any number, any ratio of I'm trying to find my calculator. Here it is. Any ratio of integers is going to have a repeating result, and you can see that on your calculator. For example, if I take 2 divided by 7, I get 0.285714, 285714, 285714, and so it's not necessarily just one repeating decimal. It may take 6, much longer. The repeat pattern may be longer than you might think it is, but they all do repeat at some point. Now, real numbers says it's the numbers that can be expressed as a decimal, which what that means is pretty much any number that can be shown by a point on the number line. So any number between 1 and 2. Just 1.1, 1.2, 1.265, 9, whatever. Those are all real numbers. It's easier really to understand better in terms of if you don't have a real number, what do you have? You don't have an unreal number, but you do have an imaginary numbers. How many people have had imaginary numbers? Was that in pre-calculus? Yeah. So you talk about imaginary numbers in pre-calc, and so for you guys who haven't taken pre-calculus, I'm just going to give you a 1-minute introduction to imaginary numbers. So if you take the square root of 4, the answer is 2, right? Because 2 squared is 4. If you take the square root of 2, you get 1.414. I think that's right. And it keeps going on. If you get the square root of -1, normally before pre-calculus you say, I can't do that. You can't take the square root of a negative number. But in pre-calculus what you do is you say that, we're going to call that I. That's an imaginary number. So it allows you to deal with negative square roots. And you're thinking, there are a lot of things in math that are stupid and not very useful, but it turns out that imaginary numbers are useful. So where are they useful? Well, it turns out that if you become an electrical engineer and you want to analyze how the voltage and current vary in a circuit, it goes up and down, it's not constant, it varies. To analyze sinusoidally varying signals and how it behaves in time, you can solve those problems using imaginary numbers. So there are a lot of places where imaginary numbers are useful. Most likely, unless you take calculus or above, you're not going to really need it. But so real numbers are ones that are not imaginary, I guess that's. And then the final one is the irrational numbers, and these are examples of irrational numbers are pi. There's e, which is another special number, and the square root, or any root of a number that's not a perfect root. So the square root of 4 is 2, because 2 squared is 4, but if you take the square root of 2, what number multiplied by itself gives you 2? Well, if I take the square root of 2 on my calculator here, I get 1.414213562. There's a lot of digits on here. 1.414213562. You'll notice there's no repetition of numbers. And actually, the exact square root of 2 has an infinite number of decimals. And there's no repeat. It just keeps going on, and there's no repeat. So when you have a number that doesn't have a repeat, which rational numbers do, irrational numbers don't. So they're the other ones that don't repeat, are irrational numbers. And the main cases are pi, e. There's one called phi, which we'll talk about later, and the square root of numbers that are not perfect squares are irrational numbers. Why do we introduce this? Because some of the problems may say list all blah 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 types of numbers, and if you don't know what those kinds of numbers are, you can't solve the problem. So okay, this is another terminology. One of the important things about sets is how many elements, how many members. So those are I used both terms there, members or elements. How many elements or members are in the set? So they give it a special name. It's called cardinality. It's just how many elements are in a set. And we use the terminology n parenthesis a to ask that question. So if we read this, we'd say n of a, which means how many elements do I have in the set, which is what we call the cardinal number. So I'm just going to give you a couple of examples. So if I said set A was this, four. All you have to do is count, okay? If I said set B was N of B would be, anybody? So what's that? 12, yeah. So you can figure that out because it's all even numbers, and so there's going to be half the number. So you take 24 divided by 2. So the answer is 12. So either, if you get a question like that, you're either going to just count the numbers that are there, like this, when they list everything, or you can kind of figure it out from what the set looks like. Bart, you okay? So you'd say the cardinality of set A is 4. The cardinality of set B is 12. But really all it is just how many elements are in the set. So the answer is, Sasha, how many elements are in that set? What is the set describing? Yes, exactly. They're 26. So we know that because we've learned that somewhere many years ago. 26 letters in the alphabet. So N of A equals 26. Okay, so you can see the kind of problems that we have to do. I'm not going to do more than one. Okay, so if I say two sets are equal to each other, I think most people would know what that means just from the gut feeling, right? If you have sets that are equal to each other, then what's in set A is exactly what's in set B, and what's in set B is exactly what's in set A. They have to come up with a mathematical description so that it's unambiguous. So this is their definition, the math definition. Set A is equal to set B, provided the following two conditions are met. Every element of set B is an element, every element of set A is an element of set B, and every element of set B is an element of set A. If you only include one, you could have one set having everything the second set has, but not every, well, let me give an example. This is an example where they would pass the first test, but not the second test. So if I had set A as being A, comma, B, comma, C, and set B as being A, comma, B, comma, C, comma, D, comma, E, I could say every element in set A is an element of set B. But obviously they're not equal to each other because this one has two more elements. So for this to be true, I have to get rid of these two, so I'm going to just erase those. So the first one's still true. Every element of set A is an element of set B, and every element of set B is an element of set A. So you go one direction, you go the other. Mathematically, that shows that they're equal to each other. The reality is, if I show you two sets, then you should just look at them and say, well, do they have the same things in them? All the same things. I mean, it's a little bit hard. Okay. Now, if I had set, let's say set C was this. So in this case, A is equal to B. We use an equal sign, just like we normally do. If I had this, I would still say A is equal. I could still say A is equal to C, and that's because the order is not important. So I can still say every element in set A is an element in set C, and the other way around. So when I do a test problem like that, don't get confused because they're in a different order. The order is not important as far as sets are concerned. You want good reviews. So anyway, that's a little sidelight on Airbnbs. It's fun. They have them in Europe too. If you ever travel to Europe or something like that, it's kind of, you can meet the people, and if you booked a hotel in Brooklyn, same night, it would have been $240 a night. So $240 versus $95. Sounds good to me. Okay. Anyway, back to math. So the order is not important, and there's the homework. So that's going to be due next Wednesday, which is the test day. So turn in the test. Let me put them on one page so you can see better. The other interesting stuff is over the weekend, my daughter and her husband went and looked at a house and put an offer in and bought it. They haven't they haven't paid for it yet. But as long as everything goes through, they have a house on Staten Island with a guest room. So we don't have to spend money staying in a hotel. They're in a B&B now. So they live in Brooklyn, but they're going to move to Staten Island, which is, she'll have to take the Staten Island ferry to work. But yeah, it has a bedroom, so that'll save us $600 every visit now because we'll have to pay for hotels. Maybe $500. So anyway, the homework problems are essentially what we've gone over in class, just different solutions. My original plan, I had this great idea. Has anybody ever taken a cross-country trip? Driven cross-country? So we haven't either, and we were going to, we wanted to drive from Covington to Utah and then see the, like Bryce and Zion National Park, and there's a lot of cool stuff in Utah. Then drive down to the Grand Canyon, see that. And I came up with this whole plan of using Airbnbs for the entire trip, and mostly spending less than $60 a night. There are a few places you couldn't get something that cheap. It's going to spend about a month. It's going to cost about $1,200 for a hotel, which really is not that bad if you think about it. Yeah, that's right. Yeah, beach for a week. So let's that all planned out. And then my daughter, Heather, she's having a baby in March. So I think our vacation, our trip has now been supplanted by the helping out. Maybe another summer. Okay, onward we go. Okay, so we're going through section 2.2 for the test. So, like I said, we'll probably won't get to everything in this chapter, but this section, but we'll get far enough, and you'll be able to see the rest of it on Monday or whenever you want to watch it after tomorrow. So the next thing we're going to talk about is more terminology. So we're going to talk about subsets. So we talked about sets, which are just a list of things that are in common, usually. Numbers, letters, states, anything we want to list. And we're going to introduce Venn diagrams, how you can look at sets relative to the totality of the possible things that could be in the set, but maybe not included in the set. And we'll talk about different kinds of, we'll talk about sets and proper subsets. And then we're going to talk about how you can have sets with common things, common elements. That's section 3. So Venn diagrams, most everybody has seen those before. So what we're going to do is Venn diagrams typically are made up of a rectangle. So here's a rectangle. And everything that fits a certain description, like the numbers from 1 to 10, the letters in the alphabet from A to M. You could define things that might have some commonality to them. The people in this class, the kind of cars that are the Honda dealer, anything, just those might be included in, we might include those in the universal set. So the universal set, we use the symbol capital U, and it's pretty much a set of all elements for a given type of something. I'm just going to say something. That's not very mathematical, but of something. Whatever that something is, letters, numbers, first names, last names, etc. And we show that graphically by a rectangle. Then we can show certain of these somethings in a smaller grouping. We show that by a circle, typically. So I'm going to put a U here to represent the rectangle means the universal set. And I'm going to use that letter A to represent a smaller grouping of that totality of items. So let's just give you an example. Let's say the universal set is the letters, small lowercase letters in the alphabet. So that's the universal set. We may say that A is the set that includes the first 3 letters of the alphabet. So if I want to show that graphically, all of the letters except A, B, and C are going to be in this part here, and the letters that are in set A are going to be inside. So you can do this by listing the letters, or whatever they are, inside the circle, and then you would do all the other ones outside, which I don't know how long it's going to take me, but I'm going to go ahead and do it anyway. I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Okay, so as you can see from the graph, all of the letters are encased in the rectangle. Only 3 of the letters are in the circle. So that's how you show sets graphically. I could make up another set if I wanted to. So I'm just going to pick another little circle, and I'm going to make it so it circles circles those 3 elements. So I'm going to call that set B, and so set B would be the letters J, K, and L. So this is B. So I'm using the capital letters for B for sets and other ones. Okay, so we'll get more complicated with, that's just a general introduction to Venn diagrams. You have a rectangle with circles in it. You don't necessarily always have to list all the elements here. You can just say this is set A and this is set B, and you could say the universal set is this, and do it mathematically instead of visually. Okay. Now, so this is basically the same diagram, except I've got one little extra piece of information. I've got this little A prime. So that is a special, what A prime represents is everything that's in the universal set, but that's not in A. So the light blue represents this. So not A, in terms of our thing over here, would be all the letters from D to Z would be A prime. So what is it? Let's just talk about that. What is A prime? I think it's on, yeah, it's a little apostrophe. So if you look at your keyboard, it's under the double apostrophe. It's apostrophe. It's not one. It's a little mark. So I'm going to redraw this thing over here so we can put this on one page. So this thing we call A. It's actually, we read this as A prime, so let's write that out. This is in your book, the definition, so you don't have to copy it if you don't want to, but A little mark is red A prime. So A prime is what we call the complement of a set. And it says for any set A, so graphically this is set A, this is the universal set. It says for any set A within the universal set, the complement of A, written A prime, is the set of elements of U that are not elements of A. That is, so we're using this set builder notation, A prime, the complement of A, is equal to the set of all X, such that X is an element, is a member of U, and X is not a member of A. So this is some other terminology we haven't talked about. So it's kind of like a big E, but more like a pitchfork. and we read that as is an element or is a member. So it's just it's a mathematical way of representing those words. So when we read this, we would say X is an element of the universal set and X is not a member of set A. Or we would say X is not a, I forget which one I used now. You use either element or member. They mean the same thing. So that's what this means. X is a member of U, X is an element of U, X is not a member of A, or X is not an element of A. Either way. Okay, so that's some new terminology. And we saw that on the previous, we saw that on the previous screen when we actually put numbers in. All these letters that are outside of A, meaning D through Z, would be the complement of A. So let's go back. We have a space here. We would say A complement of A would be D, E, F, ... Z. So the complement of A is every letter that's not in A. So that's what the complement is. Now we're going to talk about subsets. So a subset of a set, it says A is a subset of set B if every element of A is also an element of B. In symbols, it is written as A is a subset of B. So that kind of like a C with an underscore means is a subset. Okay, so here's an example. Let's say set A consists of the letters A, B, and C. Let's say set B consists of the letters A, B, C, D, E. So the question is A a subset of B? Looking at that definition. So is every element of set A also an element of set B? The answer is yes. So therefore A is a subset of set B. So we can say from these definitions of A and B, A is a subset of B. Now going the other way, if we said is B a subset of A, you would say no, because yes, A is an element of A and also of set B. These three are elements in set B, and they're also elements in set A. But D is not an element of set A, and the letter E is not in set E. So, and think of not like substitute, but lesser. So sub means, like, think of a sub-level or a substitute. That's the player that's not on the first team. So they're substituting. They're lesser. So the subset should always have the same number of elements or less than the set that we're comparing it to. So from that perspective, we know right off that this could not be a subset of that, because this has 5 elements, this has 3 elements. But this one has 3 elements, this one has 5, so this could be a subset just from a number standpoint, number of elements. And then you'd have to just check to see whether they're in there. The only one that's might confuse people is if you looked at another set called set C, and that set C was A, B, and C. So the question is A subset of C, question mark. And you might think, well, it's not smaller, so it can't be sub, right? But if you look at the definition, it satisfies the definition. It said A is a subset of B if every element of A is also an element of C. Well, yeah, they are. So we would also say they're equal to each other. So A is equal to C. A is a subset of C. C is a subset of A. So that's true. So the answer is yes. So that's true. C is a subset of A. That's true. B is not a subset of A. So to show not, you have a diagonal line drawn through it. The final one that you may think is kind of A can be also a subset of A. So any set is a subset of itself. It's like, 1 equals 1 in algebra, 1 equals 1. It seems like a trivial result, but it's still mathematically correct. So it's kind of like with sets. A is a subset of A. Oh, one more. There's one more thing here. Let's see what it is. Let's add one more page here. So we talked. I don't know if we talked about this or not. There's something called a null set, and there's two ways of representing a null set. One is to draw that, so it's a 0 with a mark through it, or you can show it as an empty set of brackets. So it's a set with nothing in it. So the question is the null set a subset of set A? Question mark. So the question. So let's ask the question: what is a subset? Is every element in this set also in this set? So you may say, well, it is and it isn't. It's kind of like 4 to the 0 power, something to the 0 power. The answer is yes, okay? So the null set is always a subset of every set. So the answer is yes. Question mark, answer yes. So specifically, the null set is a subset of every set. Because one of the options, I don't need a question mark there, I need an exclamation point or something. Okay, we're almost done here. There's another thing called a proper subset. So I'm going to skip over that for right now. Let me delete that page. Well, actually, we'll make this comment. So we said two sets are equal. There was another definition for equality of sets. All the elements in set A had to be in set B. All the elements in set B had to be in set A. That was one way of saying two sets are equal to each other. In terms of subsets, two sets are equal if A is a subset of B and B is a subset of A. So it's just an alternative way of describing that they're equal to each other. The only time that can happen is if the elements in set A are exactly the same elements that are in set B, and the other way around. Pardon me? Yeah, like A and C and the other one. So if we go back to that example that we looked at earlier, somewhere, maybe I passed over it. Must have passed over it. Where did I go? Yeah, right here. So A is equal to C because A is a subset of C. And, well, I said it right here. Yeah. Because this is true, then A is equal to C. So that's what that's saying. Okay, so let's put that on one page. There's one special it's kind of for people who they think it's weird that you can have the subset of a set being the same set, same elements as the original one. So there's a special kind of set which is called a proper subset. And a proper subset is subsets that are not equal to the original set. Okay, so there's that one case where they're equal to it. A set is a proper subset if it's any subset that's not equal to the original set. So that's what it's saying here. It says it's a proper subset if A is a subset of B but not equal to B. And we use this C-looking thing without the line underneath it. So that means proper subset. So as an example here, let's say set A is A, comma, B, comma, C. Let's say if I wanted to list all the subsets, list all possible subsets of A. Okay, so here they are. One subset would be just the set again. Okay. Another subset would be A and B, but without C. Another subset would be A and C, but without B. Another one would be B and C, but not A. We could have each one listed separately. So that would be a subset. That would be a subset. And that would be a subset. And the null set. So those are all the possible subsets of the original set, because all the elements in here are in here. All the elements in here are there. Okay, you can see that. All the elements here are in there. So these all satisfy the definition of subset. And the null set is a subset of every set. So we include that. There are 1, 2, 3, 4, 5, 6, 7, 8. If you said list all possible proper subsets, what I'm going to do, so I'm going to say underline, so I don't have to write them all again. Underline all possible proper subsets. So it's the same list except the first one, because the first one is equal to the original set. So that's the difference between proper subsets and just subsets, is that one technicality. Okay, so before Wednesday, well, the test is on Wednesday, so let's summarize what we're going to do here. I'd say before Monday, watch the videos that I tell you to watch going to Blackboard. But by Friday, by Friday I will post a review for the test. So what I would do is finish the video before Monday, after Monday, but before Wednesday, watch the review. From that, come up with your cheat sheet. And because there's no class in here, well, no, I can't do that because we're going to use the entire class, so don't worry about that. So we're going to have half an hour of class on Wednesday, then I'll give you the test. You'll have 45 minutes to finish it. That should be plenty of time to get it done. And then once you finish the test, you hand it in and you can leave. Okay. 8.5 by 11. You won't need that much. Yeah, it's not one of these little like index cards. Yeah. Oh, there's Caitlin. Okay. Yeah, just set that there.